Hi, everyone. My name is Sherin Mathews, and I'm a principal AI research scientist at US Bank. I'm here to present my session on federated learning titled Federated Learning Balancing a Thin Line Between Data Intelligence and Privacy. Outline of my talk, I would first introduce the topic and the need for the topic of federated learning. We would then follow up with the taxonomy and the system architecture of federated learning systems. We would then deep dive into the security and the training challenges involved with developing federated learning systems, and then we'll finally conclude with applications and inferences. Now, the importance of data in federated learning. Data has always been on significant private priority for businesses of all sizes, especially in financial services. Now, as the HBR article mentions, the biggest obstacle to using advanced data analysis isn't the skill base or the technology. It is plain old access to data. Now, with the advancement of technology, companies tend to capture customer data from many resources, such as tracking customer activities and even appending other sources of data to enhance the ability to contextualize data and even draw insights. However, preserving customer privacy is vital considering the sensitive nature of customer data. Now, this leads to the need for federated learning systems. Several factors have driven the global consensus to focus on data privacy preserving and security of individuals and businesses. Now, with frequent incidents of personal data breaches of individuals and even institutional data rights not being equal, there is a need for strict data privacy regulation. This is one of the prime reasons for the need of federated learning. Now, when you talk about data privacy, as machine learning algorithms traditional machine learning algorithms have exposed more of its drawbacks, finding new, secure, and effective ways to collect as well as learn from data has become crucial, thereby opening new research avenues to build personalized models without violating user privacy. GDPR protects the user privacy by requiring operant to distinctly obtain user consent and even adhere to sufficient data privacy regulations. Now, in addition to data privacy, we would look at additional dilemma called data isolated islands. Data has been foundational for building AI models. Integrating data scattered across various organizations is challenging and can introduce a considerable cost. It is important to therefore understand where data is stored and how is it processed, and make sure that it is done in a highly segregated manner due to regulatory and privacy concerns. Now, there is no doubt about the origin of this term. This is actually a pioneering work to create shared models from customers' computing devices that can be clients in order to improve the user experience on those devices. Data here is generated locally and remains decentralized. Each client stores its own data and cannot read the data of other clients. Data is not identically or independently or identically distributed. Now, traditional machine learning frameworks primarily use a centralized system to process the data using a centralized collection, unified processing, you have cleansing, and your training models, which require your training data to be located at the same server. What federated learning offers to us is a distributed machine learning architecture that solves the dilemma of learning across data silos by enabling training over multiple decentralized systems. It generates more robust models without sharing data, leading to privacy-preserving solutions with higher security and tighter access to privileged data. Now, as a concept, this is the definition that's being defined, wherein you have a machine learning setting where you have multiple entities collaborating into solving a machine learning problem under a coordination of a centralized server. Now, having a look at the overview of the entire system. Now, as I mentioned, federated learning system is a distributed paradigm that helps you to train models using samples distributed across multiple users in a network, while keeping the sample on the user device with the aim of efficiency and even protecting user privacy. Federated learning systems actually bring the model and the data model and the code to the data rather than taking the data to where the model resides, as is currently in most of the learning systems. So data remains locked on the server or even the edge device while only the algorithm traverses, so that it can be implemented across devices or across organizations as shown in this image here. Then moving on to the taxonomy. So when you're trying to build or design a federated learning systems, what are the points that you need to consider while doing that? So while considering how the training and the inference data are being distributed, existing federated learning approaches can be classified into three categories. One is a horizontal federated learning, a vertical federated learning, and a federated transfer learning. We'll go into details in the next few slides, but I'm just giving you an overview here. The next point here is to look at the scale of federation. This is another critical criteria in designing effective algorithms. Based on the scale of data and the number of client nodes, federated learning can be classified as cross-device federated learning or cross-silo federated learning. Next, privacy mechanism also plays a very important role in federated learning systems, and it offers another way, say, to group algorithms. The two state-of-the-art mechanisms for federated learning-based data protection involves differential privacy and even cryptographic methods. So when you talk about data distribution, these are the main three categories that comes into play. One is a vertical federated learning, followed by horizontal federated learning and federated transfer learning. Now, vertical federated learning is applicable where you have shared data between unrelated domains, which are used to train a global model. This can be used for cases where you have each device consisting of data set with different features, but for the same sample. To give an example, you have two organizations having data about the same group of people, but they have different feature sets. They can use vertical federated learning to build a shared model. Now, a real-time use case or example would be a scenario where you have, say, a bank's marketing team or of a credit card division. They would like to improve their model by learning some of the most purchased items from an external shopping site or so external shopping domain. The user information from the bank and the details from a separate shopping site can be shared to train the model with intermediate encryption, ensuring a restricted and a secure access to only the derived statistics. With this liaising of information, banking domains can serve customers better with relevant offers, and online shopping domains can actually revise their point allocation systems for customers using credit card transactional data. The other point is a horizontal federated learning. This approach is used when you have data sets on devices wherein they share the same attributes, but in different instances. So in this category of federated learning systems, user can have similar attributes in terms of domain usage and even derive statistical information. And it is used in cases where you have a device consisting of a data set with the same feature space, but with a different sample instance. The last one is a federated transfer learning, which is kind of similar to a traditional traditional machine learning model, where you want to add a new feature using a pre-trained model. So if you want to extend your machine learning model to a new sample instances which are not, say, previously existing, that's when you can make use of federated transfer learning systems. Now, here are some examples of how a horizontal federated learning system can look and how a vertical federated learning system can look. Now, as I said, with horizontal federated learning, you are making sure you're making use of the same set of features. The rows of the data are available with the same consistent set of features. This is exactly the kind of data which you would feed into a machine learning task. Whereas vertical federated learning is applicable to cases where you have two data set sharing, say, the same sample ID, but they differ in the feature space. This is our example of how the data distribution examples might look. Next one is looking at the scale of federated learning. So when you look at this particular criteria, the main two subcategories are cross-device federated learning and cross-silo federated learning. Cross-device federated learnings are used in case of scenario when you have a very large number of participating devices. On the other hand, when you talk about cross-silo, you might be using it when the participating devices are less in number and are available for all rounds. So the data set or the training data can be either horizontal federated learning format or a vertical federated format, but most cross-silo systems are being used for cases with organizations. The next one is privacy systems. Now, differential privacy or cryptographic methods are the two main known methods for preserving privacy. They provide the federated learning systems or servers from identifying the owner of a local update and ensuring that, say, a single record might not influence the output of the function. So what differential privacy mainly does is it adds a certain level of noise in the original local update while furnishing a theoretical guarantee on the model quality and protection against inferences attacks. Now, due to injected noises, such systems can tend to produce less accurate systems. Whereas when you look at cryptographic methods, you might look at frameworks like homographic encryption or even SMC, secure multi-party computation. Now, these parties need to encrypt their message before sending and also decrypt the message at the output end, which leads to a very high computational overhead. So the user privacy of federated learning systems is usually well protected, as cryptographic method actually ensures that the parties cannot learn anything except the output that's in place. Now, in terms of open source frameworks, now there are a number of open source frameworks that are popular. There are PySwift, Fate, TensorFlow, federated learning. There are currently a few open source frameworks for researchers and even developers if you're looking to explore federated learning solutions. PySoft is basically a Python. It's written in Python on top of PyTorch framework, and it kind of provides a virtual hook for connecting, to clients to a WebSocket. There are other frameworks like Fate and even TensorFlow Federated, which includes integration with Google Kubernetes framework, which help you to have an orchestrated interaction with clients at the server end. So now talking about what are the mainly security challenges and the training challenges. Now the topic of federated learning is still at the infancy, and it will continue to be an active area of research for foreseeable future. As federated learning evolves, so will the attack mechanism, and hence it is essential to provide a broad overview of the current challenges on federated learning. Now, security challenges include privacy security challenges that arise due to presence of an adversary who might gain access to a user device and say installs a malicious clients that gains access to a black box device. They can be targeted or non-targeted. So in targeted attacks, an adversary wants to influence the prediction of a specific task, whereas in non-targeted attacks, the adversary's motivation is just to compromise the accuracy of the model. We will concentrate on three main categories. One is model poisoning attack, data poisoning attack, and inference attacks within the security vulnerabilities categories. So mainly when you talk about inference attacks, despite I would say the substantial province of federated learning, inference attacks have demonstrated that it is possible to infer personal information from training data used in model updates during the learning system in some scenarios. So in inference attacks, an attack can infer sensitive information to which it had no granted access by querying the model several times or using some prevailing common knowledge. A commonly used method to mitigate these kind of attacks is to utilize some kind of differential privacy that provides efficient and statistical guarantee against learning for an adversary. You can add a noise to the data to obscure sensitive information so that the other party cannot distinguish the individual's information and making it impossible to restore the data, thereby rendering inference attacks ineffective. There are other defense mechanisms like calibrated domain-specific attacks and even specific data augmentation, wherein the distinctness of the model update is decremented by using a framework called calibrated domain-specific data augmentation. Also, you can run the entire framework in a trusted environment. There are also good defense mechanisms to counterattack inference attacks. So the next one is model poisoning attack. Now, a formidable challenge for federated learning is the possibility of an adversary initiating an attack to poison the local client's model instead of local data. The attacker can compromise some of the local devices, modifying the local parameters, thereby shifting the boundary of the model and introducing some kind of model errors. And this affects the accuracy of the model. For example, an attacker can include some kind of a stealthy backdoor functionality into the global model and compromise one or even several participants. It can train the model on the backdoor data using a constrained scale technique and then resubmitting the data to the resulting model and replacing the global model with the attacker's backdoor model. Now, when you're trying to mitigate or even defend against these kind of attacks, it uses you can make use of different frameworks like secure aggregation or anomaly detection based framework. Using secure aggregation acts as a robust defense mechanism, as the individual updates from each participants are actually invisible to the aggregator. So integrating these combinations are automatic and predictable that kind of helps prevent poisoning based attacks. There are other mechanisms that have been mentioned here. You can look at rejection based on error rate or rejection of the model based on the loss function, or even a combination of both. So in loss-based function, what happens is a model with a significant impact to a loss function on the global model is actually rejected. Whereas if you have an error rate based rejection model, the framework rejects the model which has a significant effect on the error rate of the global model. So these are some of the defense mechanisms that can be employed to defend or mitigate against model poisoning based attacks. Next one is a data poisoning attack. Now, in a data poisoning attack, the attacker poisons the the training data for a certain number of participating devices during the learning process. This leads to compromising the accuracy of the global model. Here, the attacker poisons the data by directly injecting the poisoned data into the targeted devices or even connected devices. And hence, it's kind of the most commonly used mechanisms in machine learning systems for data poisoning, for attacking. So data poisoning attacks also can leverage gradient descent to generate adversarial-based attacks. Now, a label flipping attack or a backdoor attack also falls under data poisoning attacks. In a label flipping attack, what happens is you have an adversary that kind of looks to alter the local data by flipping the labels of the training instances of the source class through the target class while keeping the training data intact. This might result in substantial drop in model accuracy. Whereas in backdoor-based attack, an adversary can insert some kind of a backdoor input into a local data and tweak the features that are then transferred to the local model. Now, there are existing mitigation frameworks that can be used for defending against data poisoning attacks. They include clustering-based models or even fool's gold algorithm. Now, what clustering-based algorithms do is they check the model updates at the aggregator level and then cluster them into two groups using dimensional reduction algorithms. Clusters identified with, say, less than n by 2 clients are placed in a suspicious cluster of malicious clients and then perused for further investigation. The other method is the full squad scheme, which proposes limiting potential malicious clients' contribution with similar models to the global model by reducing the learning rate. And then we can move on to the training challenges. Now, training challenges mainly encompasses those issues related to high dimensional models. Sorry, there is a typo here. So the main issues I would like to focus on is dimensionality. The adversary here can make, say, minuscule and even detrimental changes in the high dimensionality model without being detected. So sharing a model parameter might not be an ideal design choice in federated learning systems, as it opens like the model's internal state to inference attacks and maximizes the model's malleability by poisoning attacks. So exploring whether sharing model updates is essential is worthwhile to address the fundamental shortcoming of federated learning systems. So sharing less sensitive information or only sharing, I would say, the model prediction in a black box model can result in a more robust, privacy-protected system. The other training challenge is looking for optimization mechanisms. Now, federated learning systems actually incur a huge computational cost when deploying defense mechanism. And hence, it is important to identify an adversary attacking the system. So in addition, disparate defense mechanism might have different effectiveness against various kind of attacks. So they might have different cost. Therefore, it is kind of crucial to understand or study the optimization methods used for deploying different mechanisms. And there are frameworks that can be used like game theory methods. They actually hold excellent promise in addressing these kind of challenges where you're trying to optimize for different defense mechanisms. Next one is looking at decentralized federated learning systems. Now, potential learning frameworks for potential federated learning frameworks for collaborating among businesses that do not rely on or trust on any third-party devices, as no centralized system is required in the system. So in this criteria, each party can be voted in a server in a round-robin manner. So sharing model updates is currently, I would say, limited to homogeneous federated learning architecture. Hence, it is compelling to understand how to expand the federated learning system to train models with heterogeneous architecture and to investigate if the state-of-the-art privacy techniques are suited for this heterogeneous federated systems. Now, in terms of open areas research, I think federated learning systems contain a lot of hyperparameter tuning, say the number of epochs, the local number of clients, the client dropout probability, which vary from algorithm to algorithm, which makes it hard to benchmark the actual non-IRD performance on these models. So you can look at frameworks where there are a few real image data sets that have been proposed. But a universal, I would say, homogeneous or even a heterogeneous benchmark data set has not been emerged in the field of federated learning. And having research in that direction is great. You can also look at synthetic data generated by arbitrary data partitioning. They are not being, I would say, effectively able to evaluate the performance of the method. So looking at these criteria of having additional quantitative criteria to measure the degree of privacy and looking at additional benchmark frameworks that actually reflects the real world's problem to compare federated learning systems effectively are still open areas of research that can have in further investigation. Now, to kind of look in the finance space, like how this could be applied in various domains in the finance industry. So, federated learning systems maintain client confidentiality relating to portfolio components and have been used to optimize expense ratio and even pricing for portfolio management in banking and financial services. These techniques allow managers and even financial advisors and robo advisors to connect with other investment bankers, which can provide a fair purchase price while buying or even selling, portfolio. Another application is looking at loan risk framework. Typically, banks have been using whitelisting based frameworks to rule out customers using credit card reports from central banks. Now, factors like taxation or reputation can also be used for risk management by collaborating with other financial institutions rather, and e-commerce platforms. Federated learning systems can actually help you build a risk assessment machine learning model to keep the customer information private among organizations. Banks can leverage federated learning systems for credit risk management. Several banks can join forces together to learn a total credit score for a customer without sharing the data. So, with the development of research in federated learning, many companies or even research teams can establish various tools oriented to federated learning based research and subsequent product development. Additionally, federated learning systems can also be used for, curbing unlawful financial activity like money laundering, fraud detection, in coping with financial crimes, and deep regulatory compliances like GDPR. Federated learning techniques can improve this by enabling a shared machine learning system without sharing data. Now, the last, I think, and not the least, I think another important avenue here is looking at open banking system. Open banking empowers individual customers to own their bank data without substantial potential benefits of customer experience and even revenue. I think the most impressive aspect of federated learning is its ability to decompose the model's training into distributed nodes and even a centralized server without collecting private data. Now, this kind of disintegration has a great potential to protect user privacy and sensitive data, and therefore it combines naturally with open banking marketplaces. So with federated learning, it's foreseeable to have decentralized data ownership in the finance sector, and thereby it can help boost a new ecosystem of data marketplaces and financial services. So to conclude the whole talk, I think I wanted to kind of introduce this topic of federated learning. I know it's a relatively new field with new research opportunities for making privacy preserving AI systems better. Now, as research in federated learning is still at its nascent stage, we are at a pivotal stage in shaping the developments in this area. I provided an overview of the existing, system abstractions, building blocks for federated learning systems. We also presented, say, the open source tools that can help facilitate the reproducibility of federated learning systems and even dissemination of new solutions. This includes challenges related to system heterogeneity, data privacy constraints, statistical heterogeneity. And the work kind of overviews the open areas also, like which when you talk about security challenges and looking at the training challenges and how we could look about mitigating those effects. We also proposed some kind of discussions which can help to develop full-fledged solutions for data privacy via federated learning. And finally, we also outlined the applications of federated learning systems within finance and a few handful open problems. And we hope that helps promote interdisciplinary efforts. With that being said, this concludes my talk, and happy to answer questions on this. Thank you.